Okay, let's talk about marks and channels. So, remember from last time we talked about this idea that with a nested model, we would think about visual encoding in terms of going from domain to abstraction level to the idiom level for visual encoding and interaction to the algorithm level. So, today we're really going to focus on this question of the idiom level. How can we systematically analyze visual encoding idioms? Well, let's start by looking at some really basic chart types, right? Bar charts, scatter plots. How could we systematically analyze this kind of structure? We're going to use this idea of marks and channels. And with marks, we want to represent items or links in our data. Remember, we talked about data abstractions, so I have this idea of items of data. And then we want to use channels to change the appearance of marks based on the attributes. Again, that was an idea we talked about back in the data abstraction section. Okay, so what are these marks? Well, let's think of these as basic geometric elements. Um, we could have points. We could have, let's think, I'm going to call them paths. You might think of these as lines. We could have things you might think of as two-dimensional areas. I'm going to call these polys. So these are elements we can use to represent items of data. There's also 3D volumes. In this course, we're really not going to get into that, so I'm not going to talk about that in any more detail in these lectures. So let's take this idea of a poly and actually notice there's a relationship between a path, which is a line, but we'll think of that as an open line, and a poly, which has a path around it. It's got a boundary. So a closed path is the boundary of a poly. So polys have both boundaries, which are like paths, and interiors. Now, another important thing to notice is that both paths and polys represent many items of data, right? If we look at that path, it's got that squiggly line, and that's actually representing many different data points or data items. Same with the polys. Whereas in contrast, a point is representing just a single item of data. And that's a pretty important distinction, as we'll see. Now, there's one thing that so frequently occurs, we're just going to have a shortcut. It's basically a degenerate case of a path, which is a segment, which is where we just have two items. So in general, a path is a multi-item line, and a segment is just those two. So of course, you could decompose a path into a bunch of different segments. Usually, we'll reserve the word segment for when we're talking about just this two-item set. Now, that was marks for items. We could also have marks for links. Remember that links represent connections between items in a network data set. Um, so we could literally draw the link, as a line between two things. So we're going to think of a connection as something that we conceptualize as a segment in terms of the mark type. Now, that's not the only thing we can do. Links are in general an idea of a network where we have connections between things. In the special case of a tree, which is a network where every child has only one parent, we could also think about showing that hierarchical structure with one of these polys. So a poly can be an enclosing mark, a containment mark. So in addition to those marks as items, we can also have marks as links, either as segments that connect or as polys that contain. Just for the record, containment can be nested. It doesn't just have to be a single level. Here we have a fairly complex, what's called an Euler diagram, where there's actually these multiple levels of containment. So we're showing a multi-level hierarchical structure with containment here. Now, what about channels? So the idea is that channels are controlling the appearance of the marks, and it's in some way based on an attribute value. So maybe it's proportional to that attribute value. Now, there are many, many names people use for these things. I'm calling them visual channels or channels for short. Other people call them visual variables or retinal channels or visual dimensions. Um, a lot of choices. We have position, horizontal or vertical, or the combination of both in 2 dimensions. We could use symbols to represent things. We could have size coding, either in 1D or in 2D. We could color code. We could orientation code. So we have a lot of choices. So putting these two ideas together, marks are these geometric primitives. We can have points, segments, which is the special case of paths, and then polys, which is where we have a closed path, so we have a boundary and an interior. And then we've got these channels that are controlling the appearance of the marks. Well, the key thing to know is the channels are not identical. They actually have really very different kinds of information that can be conveyed to the human perceptual system. So both the type of information and the amount of information depends very much on the channel. So let's go back to this idea of analyzing an idiom structure as some combination of marks and channels. So what about this bar chart? Well, we seem to be using vertical position, right? It's up and down. That's meaning something. Our mark type is one of these segments where we've got those 2 points. Um, what else could we do? Well, with a scatter plot, we could use separately vertical and horizontal position. And in this case, our mark type is a point. Well, we could keep going. We could add another channel. So we still have a point mark, but now we're color coding it. And we could size code as well. So let's think of this as a 2-dimensional size and area coding. So that was just a few simple idioms. We can do things like use more than one channel at once for the same attribute. That's what's called a redundant encoding. Um, The good thing about redundant encodings is it sends a stronger message. Your perceptual system is getting the same information through multiple channels. That means typically you are able to react with a stronger perception of that. But of course, it uses up those channels, so you are not free to encode as many attributes because you're using more than one channel for the same attribute. So it's a trade-off. In this case, what we see is a bar chart where we're not only coding with length, that is vertical position in this case, but we're also coding with luminance, right? The bars are getting darker as the bars are getting taller. Okay. Now, there's a big question, when should we use which channel? So a lot of the visualization theory is all about trying to give us some traction for this idea. Two big ideas. One is expressiveness, that we should match the channel type to the data type. And the other is effectiveness, which is that some channels are actually better than others in terms of being able to convey information. So the key idea with channels is that we can actually rank them according to how the human perceptual system responds to them. So there's a few things to notice here. One is I have these two columns here. That's not a coincidence. I've actually separated the channels into big categories. The so-called magnitude channels are good for conveying ordered information because they're actually giving you a perception of how much of magnitudes. So things like positions, orientation, areas, even colors, these are all something where we can perceive how much of something. Now, the other possibility is the identity channels. These are a really good fit for categorical attributes because they're not telling us how much. They're telling us what. Is it this or that, right? Is it yellow or blue? Is it a triangle or is it a circle? So as opposed to how much for the ordered attributes, we've got the what is it for the categorical attributes. So this key idea of expressiveness is that we want to match the characteristics of the channel and the data. So that's one big idea. Now, remember, not a coincidence, we talked about the attribute types. So the attribute types where we also have this idea of categorical and ordered, the reason we think about data in this way is because of how the human perceptual system works, that we really do have these two very different ways of processing data that comes in through our visual system. Now, there's also an effectiveness idea. This is And it's ranked in the sense that the up and down position of these channels is corresponding to rough categories of how accurately can humans decode the information that the visualization designer has encoded using these channels. So these differ. Um, we're going from most effective at the top to least effective at the bottom. And one really important thing to notice here is that something to do with spatial position is both ranking very high with the magnitude channels for the ordered data, both quantitative and ordinal, and also for the identity channels in terms of grouping things into spatial regions. So we'll be talking quite a lot about everything that has to do with position because it is so fundamental to how we perceive patterns in the data. Now, so far I've been talking about marks that represent items, marks that represent links. I want to take just a minute to talk about this idea of grouping, that our perceptual system can fundamentally show us not only this idea of linking things, so marks as links, the containment polys, and the connection segments, but we can also use these categorical attributes with the identity channel to convey information that's automatically processed by our visual system that also leads us to conclude that things are similar to each other. One is that proximity, that is similar spatial region. If you're in the same spatial region, you perceive that as being highly connected. And also any of the other categorical channels, if you just have the same value, like everything of the same color, or everything moving around in the same way, or everything shown with the same signal, those also convey fundamental information about grouping to the perceptual system. Now, let's talk in a little more depth about position. So, to start out with, I already alluded to the idea that there's vertical and horizontal. Well, actually, it's a bit more complicated than that. One possibility is that we have a Cartesian coordinate system, a rectilinear coordinate system, where we've got a vertical dimension and a horizontal dimension. This is very common. You can think of this as then just being a rectilinear grid. And we often use particular words. If we mean one-dimensional size, we could typically say length, and maybe it means either one of those. Often, if we say width, people are talking about horizontal, or height, they're talking about the vertical. Um, but the key thing is this is a coordinate system with a 90-degree angle between the two axes, and they meet at an origin point. There's another possibility. Thinking about a math class you've possibly had, there can be polar coordinates. Sometimes these are called radial coordinates. And in the polar coordinate system, we still have an idea of an origin. The origin's in the middle rather than in one of the corners. And that middle origin has a radial distance away from the origin, for one. And then there's an angular position. So we go around a certain amount by an angle, we go out a certain amount along a ray at that angle, and that gives us a two-dimensional coordinate space. Um, and so this idea that we could either have vertical and horizontal, or we could have radial and angular, but we can't have both at the same time. They're mutually exclusive. So typically we pick one, Cartesian or polar, and then once we've picked one, the others are not available to us anymore. So it's an either or kind of a situation with our coordinate system for any given moment. Now, another thing to notice is what are the relationships between these things like position and size? Um, Now, position is an absolute number. The way we positions, think of that as a shortcut for saying absolute position. It's an absolute position that some collection of marks have in common because they have a shared coordinate frame. Whether or not that's the Cartesian rectilinear or the polar radial, we're thinking about position as being a statement about a common coordinate system that all of the marks are sharing. Now, what's interesting about that is there's implications. There's also this idea of order, like is something above or below vertically, or is it to the left or to the right horizontally? Now, if we use absolute position, we sort of we get ordering for free. It comes along for the ride. Absolute positions always imply that we have an ordering based on exactly that same attribute. There's a similar situation with size. Um, if you have absolute positions, well, then that certainly implies something if we've got things like segments or paths or polys. That implies something about the size because we can just do arithmetic to get that from the various positions of the pieces of it. If you don't have absolute position, you could simply use size, right? You could have length coded lines. They could just be in space. You don't necessarily communicate anything with their absolute positions, but you could still read off when is one bigger or taller or shorter than the other. So we can attend to size as a relative quantity. We can attend to the order of something vertically or horizontally, or in fact, even using polar coordinates angularly or radial distance wise. So we can attend to order and size if we don't have position, but if we do have position, then we always get order. And if we have mark types that aren't points, then we get size. Notice how, for example, in this bar chart here, um, vertical, right, that in that vertical direction, we've got all three things being shown the same attribute. The actual absolute position, that shows the attribute. The order, right, we can see there's taller bars and lower bars. That order also comes from that same attribute. And the size is the same attribute. The actual length of the lines is a one-to-one mapping with the position of the top of those lines. Now, as we want to try to analyze things with marks and channels, it's useful to think beyond just the simple mark types I've talked about, right? So I talked about point and segment and path and poly. Well, you might have some interesting thing to do where you have more than one mark to show an item. These are typically called glyphs. Now, a really simple glyph could be something like just a very simple arrow, right? Because if you think about it, an arrow, well, it's got directionality, right? If I've got a point on one end and then a segment and then this little arrowhead on the other end, that's actually showing me the direction. So that's more complex than just a single segment, which is really just something where we can't tell the direction of it. There's much more complex glyphs that are possible as well. Here's my little Sharpie diagram of one. Um, but here's an example of actually what that came from. This is an example of a fairly complex glyph where they're trying to encode a lot of different uh, attributes and data all at once. So one kind of mark is showing, is it a virus or a fungus or an animal or bacteria? In this case up here, it was a fungus. Another one is in the middle is some complex little orange glyph there showing population sizes. There's also whether or not the background is colored or white. There's what color that in this case the fungus one is. So see how there's a bunch of different marks that are all coming together and they're showing just one item of data. And then of course you can have many, many glyphs, just like you can have many, many marks. So we can think of these compound, think of a glyph as just a compound made of many marks. Um, Now, there's also the ability to have a hierarchical structure. You might have some smaller marks that build into a larger mark. So you might want to take into account what level the mark is at. So within a glyph, we can think of all of the marks at the same level. These are just like sister marks. But then there could be parent and grandparent and great-grandparent marks if there's also a hierarchical structure. So we can think about the level a mark is at, and we'll just start with the smallest, most low-level marks as being level one, and then we could build up from there. And we could have more than one mark for an item, and in that case, if we want to analyze it, we're going to go through and analyze each of those marks, and we can just say a bunch of these marks in the same glyph are all at the same level, say level one. So let's go back to that example, but let's look at a few more. So before we did see this idea that we have a scatter plot. Um, Okay, so we have those points which are horizontal and vertical. And now that we've talked about order, we can realize we have both position and order horizontally and vertically for the scatter plot. And then we had that example where we added size coding, that is 2D size and area, and then we added color. So that's the column on the left. What about some other charts? Now, if we just have a bar chart, then all we have are these line segments, and those are happening only vertically, right? So we have vertical position and order and size. Uh, but let's do something where we have a more complex glyph. It's not going to be that complex. It's going to be what's called a lollipop chart, where not only do we have the line segment, but we have a point on top. From an analysis point of view, we're going to separately analyze the segments and the points. We can consider them both to be at the same level, so they're sister marks within the glyph. And so, just like we already saw the segments, it's essentially putting together that scatter plot and that bar plot. That is what we get with the lollipop chart. Notice how the points are being encoded both vertically and horizontally, whereas the segments are only being coded vertically. Now, we don't have to do it this way, right? Imagine that you actually encoded the segments going the other way. So you could instead have a segment going horizontally along, even as that point is going both horizontally and vertically. And now, of course, obviously what that's doing is it's drawing your attention either to the horizontal or to the vertical, much more so than with the scatter plot, where without the point, with just the points and no lines, you are much more likely to attend to both of those values at once. Whereas with the bars or the lollipops, you're really focusing much more on one aspect of the data, horizontal or vertical. Now let's look at what we have with the line chart. With the path, again, we could just have that path, or we could superimpose points and path together. So in both of these cases, it's horizontal and vertical. Notice how it's position and order. We're not counting this as having a size. Um, because it's not actually size coding the same way that that bar chart did. Instead, we are able to follow the line. Um, and notice how the line could be piecewise linear, right? They could be straight line segments. Segments could have arcs or curves on them. And we're just considering them both different varieties of line chart. Now, what if we take that line chart and now we drop down some lines and we go to the bottom and we fill that in? Well, now that's a filled area chart. Remember, we have the closed path. So with the line chart, we had an open path, this sort of triangle shape. And once we close that off, now we've got a poly that's got an interior. Um, and again, that's basically using horizontal and vertical position and order. Now, the thing I want you to notice, of course, is on this slide, we've got the same data, right? The scatter plot, the bar chart, the line chart, the filled area chart. We're seeing these different variations of what are some of the ways we can take those same data points. And what I'd like you to notice is where your attention is being drawn, right? We already talked about the fact that with the scatter plot compared to the different orientations of bars or lollipops, you're able to either focus on both horizontal and vertical, or much more on the horizontal or much more on the vertical. With the line chart, we're focused much more on that shape, the shape of that curve that's made by um, going from point to point. So we're emphasizing a different part of it. And then, of course, with the filled area chart, what's being emphasized is that, what we're calling a poly, that area, so that two-dimensional shape. So even though the data is the same, your attention is being drawn to different aspects by your choice of mark type. So, can we do anything we want, anytime we want? Well, actually, no, we can't. Some marks do have constraints. So let's use a geographic example to start thinking about this, because this is the easiest one to think about. So the fancy name for a geographic map, where we're color coding the regions according to some attribute, a quantitative attribute typically, is a choropleth map. So here's a choropleth map of the US. Now, it happens to be showing the unemployment rate for a particular year. If I want to take California, I used to live there, so let's pick on California. If I want to take some additional data set, say not just unemployment rate, but maybe population, what could I do? How could I encode that? Can I just shrink California or grow it? Well, no. Then, it would include Nevada. Or, suddenly there'd be a big gap between Nevada and California. That's not how the world works. Can I translate it? That is, change the position channel? No, I can't put California on top of Texas. Again, that's not how the world works. I can't rotate California. I can't turn California into a triangle and change its shape. That wouldn't make sense given the meaning of this data, right? That boundary, right? These These are actually polys. They have these boundaries, which are these closed curves. So the meaning of the data set is that boundary. So you can't just change it. In particular, the constraint is that these marks have shared boundaries. That has meaning. You can't just independently change the position or the order or the size or the orientation or certainly the symbol, the shape of it. Now, you could change everything simultaneously, right? There's some complex algorithms called cartogram algorithms that actually do change all of the geographic regions all at once. We'll talk about those in a later week. So typically, you could do with an algorithm, you could change everything all at once, but you can't just change one of them. So it's not just an issue for choropleths, it's an issue for all kinds of things. Let's imagine just this simple matrix, this grid, where, what are you doing if you've got a grid? Well, you've got a bunch of horizontal shared positions. The right side of one is the left side of the other. The top of one is the bottom of the other vertically. So a simple two-dimensional grid really does have shared constraints. Every one of those cells is in a location that can't be moved around. So it's actually quite similar to the choropleth map. Um, Now, in the matrix, we can really think about the horizontal shared boundaries and the vertical shared boundaries because they're uniform across in those dimensions. Let's take another example, a stacked bar chart. In a stacked bar chart, you've got these segments. So that means that each bar is actually a glyph made of these multiple colored segments. And there is something shared vertically, not horizontally, but vertically, each one of those segments exactly touches the one below it. So we'll talk more about the implications of that design when we get to talking about tabular data coming up in a upcoming week. But what I want you to notice is this is an example with one shared directional channel. So it's only shared vertically as opposed to the grid, which was shared in both directions. And then here's another few examples where it's not just, say, the latitude and longitude like we had with the geographic regions. We've got these more complex shapes where we can't really trivially decompose them into horizontal and vertical. Again, we'll talk more about tree maps later on. What I want you to notice is it's possible to have shared boundaries that are intrinsically two-dimensional as opposed to separately addressable vertically and horizontally. And in that case, we'll think about having shared 2D boundaries. So this idea of constraints is actually going to help us with our analysis. We want to think about when it is that the marks or the channels actually impose constraints on a visual encoding. When does the type of the mark or the characteristics of the mark actually constrain what channels we can use? When does using one channel constrain another channel? So let's think about this in terms of, is the channel available? So in some visual idioms, we've got data that's encoded. We've directly used a channel to encode an attribute. It means something. We can actually decipher this. It makes sense. And of course, as we already talked about, multiple channels could be directly used for redundantly encoding. Now, it could be that a channel isn't being used, and you could go ahead and encode something else with that in a way that doesn't destroy the meaning of what you're already seeing. So without changing the usability of an existing encoding, there could be channels that if you want to add additional attributes, you could use these channels. Now, it's also possible that some channels are unavailable, right? They're taken. You can't encode because something else is already happening in a way that gets in the way of using them with some other data. So, could be because of the mark type or the mark characteristics. It could be because that's what the algorithm or the idiom does. That's how it's designed. Or maybe it's because other channels are used. So let's step through those possibilities. Here's a nice one. We've got a data set about dogs. There's a whole bunch of questions about dogs. Um, and we've encoded this. Looks like one of these radial kinds of layouts where we've got distance from the center and then an angular position. We've got these. So essentially, this is like a grid, but it's a radial grid. Now, Does the channel of size actually encode an attribute? Well, there's two ways we could think about this. If we said yes, I mean, look, the sizes are different. There's some big purple boxes for Bernese Mountain Dog, and there's some much smaller boxes for St. Bernards. So, depending on where you are along that radial distance, the size of these boxes is actually different. Now, if I ask you what that means, well, you could tell me it's the dog name because these dogs seem to be laid out in alphabetical order, roughly, up and down here. But there's another answer, which is no, that's silly. That's not actually meaningful. It just emerged from the layout choice, right? If you'd picked a radial, I mean, this is radial. If it were rectilinear, all those boxes would be the same size. So there's some way in which it's not really encoding an attribute. Um, so maybe there's a way to think about this that's easier, right? Which is what if I just ask you, could I use size to encode something else, right? What if I wanted to encode the population of dogs in Canada? Now, it wouldn't work, right? Because these are already different sizes because of this choice of the radial layout. It's taken. We can't, in addition, go ahead and encode with size, not without changing this idiom substantially. So the way we would think about it is that here the size channel is unavailable because of our choice of radial layout. So, what we're going to think about is how it is that we could go through any existing idiom and analyze it in terms of marks and channels. So, we've already talked about the level, right? If it's a hierarchical structure, low level, high level. We've got these mark types of point, segment, which is a special case of path, and poly, which is like a closed path, an area. And then we can think separately about, well, in just one dimension, either we could be Cartesian or we could be polar. And then if it's Cartesian, it's horizontal, vertical. If it's polar, it's angular and radial. And then we can think about these things we just talked about. Are there shared borders in that direction? Is position being used? Is order being used? If position isn't, is size in use? And we can think about those for each of these. We could also think in the case of two dimensions together. Are we size coding with area rather than size coding in just one direction or another? Are we using orientation? We'll be talking much more about color later, but we can decompose that into three hunks. Are we using any of those? Are we using symbols? This isn't the complete list, but it's a fairly substantial list for a lot of the idioms that you're going to see. And so you could imagine that if you were, for each of these kinds of marks, you could go through and say, all right, let's fill these in. What's encoded and with which attribute, what's free and what's unavailable. Now, let me just mention one thing to wrap up is we've made some simplifying assumptions. We're talking about things as if there's always at least one mark per item. Now, we're also talking about an assumption that we just have a single view in which we're encoding our data. As we get further along, we're actually going to relax both of those assumptions. So later on, we're going to talk about a world where we have some items that don't have their own marks. And that's going to be using aggregation and filtering. We're going to talk about the idea of multiple views. So it's sort of even more complex than this idea of a glyph we talked about. We're going to talk about actually having multiple views, often side by side. So that's coming up. But for now, we're going to stick to what we can analyze with both simple marks and compound marks of glyphs and our visual channels, because that's a base for thinking about visualization.